A star is essentially an enormous ongoing hydrogen nuclear bomb that is constantly exploding at all different places within it. It works almost like an oven, heating up the gas inside it to ridiculous temperatures, which causes it to undergo changes that release an enormous amount of energy. To be a bit more specific, hydrogen atoms smash into each other at speeds close to the speed of light and turn into helium atoms. This is a very violent setting, and the peaceful picture we get of our sun on a nice blue sky day is just thanks to how far away it is from us, and thanks to our atmosphere absorbing most of the energy that comes our way. In our universe, we encounter stars of all different kinds, and in the last video we saw the different stages of life that we could see a star in. And here we're going to look at a star's characteristics. The two characteristics we are usually interested in are a star's temperature and its brightness, and from these we can figure out its size. Figuring out the temperature of a star from light years away may seem a daunting task, but we exploit a handy bit of knowledge to calculate it. This knowledge is that things look a different colour when they burn at different temperatures. Blue fire is hotter than red fire, and we know the spectrum of colours that stars shine and their corresponding surface temperatures. We therefore classify stars by seeing what colour they shine and deduce how hot they are at their surface. The surface of our sun is about 5,500 degrees Celsius, and it looks pretty yellow. To appear blue, the surface of the star would need to get above around 12,000 degrees Celsius, and we do indeed see stars this hot. Moving on to the brightness of a star, we must first specify what kind of brightness we mean. Do we mean how much light the star produces, or how much light we see of it here on Earth? The difference is evident when we look at our sun. To us it looks like the brightest star in the sky, but we would be naive to think that it actually produces more light than any other star in the universe. The problem is clearly that things look brighter when they are closer to us, and so to distinguish between close and bright, we introduce two different variables to describe brightness. We have the apparent brightness, a measure of how bright a star looks to us on Earth, and absolute brightness, a measure of how much light the star actually gives off. Another way of describing the absolute brightness would be to say, how bright would each star look to us on Earth if they were all the same distance away? The sun lies at the top of the apparent brightness list because it's the brightest thing we see in the sky. But it's quite mediocre in the absolute brightness list, since if it were the same distance away as the other stars, we wouldn't expect it to be particularly bright. It's quite an average star. Now I can draw the most important graph for classifying stars. It's called the Hertzsprung-Russell diagram, or just HR diagram for short. Along the x-axis we plot the temperature, starting from hot on the left, going down to cool on the right, which corresponds to blue stars on the left and red stars on the right. Along the y-axis we have absolute brightness, with the most intrinsically bright stars at the top and the dimmest ones at the bottom. Note that this is absolute brightness we're using here, not the apparent brightness. Recall the stages of a star's life from the last video. Out of these stages, by far the most numerous we see in the sky are main sequence stars, along with red giants, supergiants, and white dwarfs. Neutron stars and black holes are far more rare, and they're naturally very hard to find. Our sun is a main sequence star and finds itself around here on the HR diagram. The other main sequence stars generally occupy this diagonal here, starting from cool and dim up to hot and bright. The white dwarfs are very hot, but small and not shining like a normal star anymore, and so they find themselves down here in this corner on the diagram. Red giants are very bright since they appear huge, but since the outer layers have actually expanded and cooled, the star's surface isn't actually that hot, and so they go around here on the diagram. Red supergiants are even brighter, and can actually be hot as well as cooler because of the intense collapse happening within it, and they occupy this top band. These are the important features on an HR diagram worth remembering.